Hey, what's up guys, and welcome back. In today's video, we're going to be building Engine Simulator's fluid simulation and visualization system, and then using this system to simulate a trumpet. Before we get started, I'd like to thank BeamNG, Reina, Meister, Goldwolf, and Snow for supporting me at the Master Mechanic level on Patreon, and NordVPN for sponsoring this video. My wife and I have both used NordVPN for the past 4 years, so well before they reached out for this sponsorship, and my own personal experience using NordVPN has been pretty positive. It's easy to use and also very fast. But I did do some research into exactly how VPNs work before actually recommending it to you guys. There's a lot of confusion about exactly what VPNs do and how they can be useful. All you really need to know is that connections to most modern websites today are going to be encrypted via HTTPS. However, the websites that you visit can still be tracked, and this information can be sold by your ISP. And they very likely already do that. NordVPN prevents your ISP and potentially other bad actors from accessing and profiting from this data. You can also use a VPN to change your virtual location, allowing you to access content that wouldn't otherwise be available in your region, which can be especially useful when traveling. Try NordVPN risk-free for 30 days using my exclusive link, nordvpn.com/ontothegreat. Thanks again to NordVPN for sponsoring this video. Last time, I simulated a steam whistle using Engine Simulator's fluid simulation. To keep things simple, I'm going to refer to this fluid simulation as the legacy model. Some people pointed out that real steam whistles don't have springs or pistons or any other mechanical elements to achieve resonance, and this is true, and I'm aware of that. These virtual elements are necessary because the legacy fluid model is too coarse to model the complex acoustic phenomena inside the steam whistle. We're going to revisit this problem today, but this time with a slightly different musical instrument, the trumpet. The most challenging aspect of Engine Simulator is the requirement that it runs at or near real time, which seems to rule out a lot of the more advanced fluid simulation techniques. In fact, just running in real time isn't even enough because we need to also generate real-time audio, which is usually sampled at 44 kHz or higher. That means we need to run the fluid simulation at least 44 kHz, or we'll start sacrificing audio quality. Most physics engines in games run at the game's frame rate or a little bit higher, so 60 to 200 Hz. Some games with more sophisticated simulations like BeamNG can run at around 2 kHz. The core idea behind the legacy fluid model is to simplify complex 3D elements into control volumes or cells. An intake runner, for example, is modeled as a rectangular prism with uniform temperature, pressure, and velocity inside. This is obviously a massive simplification, and a lot of the complex fluid behavior inside the volume is lost, but it can still make some basic predictions about airflow. Most real fluid simulations subdivide the simulation domain into multiple control volumes, and the more control volumes you have, the more accurate the fluid simulation will be at the cost of being a lot more performance intensive. Considering that Engine Simulator already uses the smallest possible resolution of basically 1 and stresses even high-end CPUs, it would seem like increasing the resolution while maintaining any kind of decent performance isn't possible. But there are some ways that we can get around this. First, we need to familiarize ourselves with this equation. These are the Euler Equations for compressible flow stated in vector form. This is a partial differential equation, and more specifically, it's a hyperbolic partial differential equation. Both partial differential equations and computational fluid dynamics are complex fields that I spent months researching, so I'm going to be talking about it in a very simplified way. For those interested in studying more, I left some links in the description to some excellent sources. Performing a fluid simulation is essentially equivalent to solving this partial differential equation. To do this numerically, we need to first discretize our domain. And in this case, we're performing a one-dimensional simulation, so our domain just looks like a line, which represents a single length of tubing. We can subdivide this line into cells, where each cell records its own internal state. We're concerned with 3 state variables, which are mass, momentum, and energy, which are all conserved quantities. At all times, the sum of these values across the domain must not change. And this makes sense, because we wouldn't expect the total mass of the system to change if there was no mass flowing in or out of the domain. A similar argument can be made for momentum and energy, which are also conserved quantities. An interesting property of this differential equation, which is extremely useful for optimization, is that the speed of causality in the solution is not infinite. So a disturbance at one end of the domain will not instantly affect the other end. This is not true for things like the heat equation, which predict that heat disturbances will be felt across the entire domain instantaneously. Instead, the disturbances travel at the speed of sound, unless of course the fluid is moving supersonically, but we're not going to deal with this situation very often. That means that if we size the cells in our discretization intelligently, they become completely independent from each other, and this allows you to simulate them in parallel, which is perfect both for running on the GPU and multi-threading on the CPU. CPUs have special instructions called SIMD instructions, which I talk about in some of my other videos. They allow the CPU to do multiple calculations at the same time on the same thread. Using AVX, or Advanced Vector Extensions, we can run 8 simulations in parallel on the same core. This is exactly what I've spent the past 2 months working on. This is my fluid simulation library called Tubular, which will power Engine Simulator. It is fully multi-threaded and features AVX support. It can run fairly sophisticated simulations in real time and produces samples fast enough to generate real-time audio. The spatial resolution can also be adjusted trivially to reduce CPU load on cheaper hardware. Let's look at some examples. Each slice represents a cell in the simulation domain, the radius represents the pressure, and the color represents the temperature. We'll start with a stereotypical example of a shock tube. A shock tube is just a tube with two halves which are separated by some sort of barrier or membrane, and the two halves don't interact with each other. The air in the two halves are held at different temperatures and pressures, and then are suddenly allowed to collide with one another, maybe by removing the barrier in the middle. This initial condition is called a Riemann problem, and conditions like this are used in the real world to test CFD algorithms. I was surprised to learn that fluids do not behave intuitively in these conditions and produce a very strange and interesting pattern that you wouldn't really expect. Eventually, the two halves will equalize to the same state and things return to normal, and it's a little bit more understandable. We can also use Tubular to simulate musical instruments. To understand how this works, we need to understand standing waves in a pipe. In this demonstration, I have a single length of pipe with a wall on the right side, and on the left we have a pulsating pressure source. Notice how the pressure waves propagate along the tube, then bounce off the wall and return to the origin at the speed of sound. If we tune the pulses just right, they will return to the input in sync with the oscillator, making the wave now appear to be standing still. You may have figured out by now that by varying the length of the tube, it will change how long it takes for the sound signal to travel from one end to the other, and this will change the resonant frequency of the tube. This is exploited in instruments to play notes with different pitches. This effect also works if the end of the tube is open. It might seem counterintuitive that the pressure wave bounces off of nothing, but this is actually what happens in real life. It's a bit hard to understand in one dimension, but in 3 dimensions, you can imagine pressurized air in the tube suddenly meeting an essentially infinite pressure sink in the atmosphere, which causes it to lose pressure rapidly as it expands outward. That sudden pressure drop is a disturbance like any other and produces a wave in the opposite direction towards the left side of the tube. A trumpet is essentially a tube with one closed end and one open end acting as a handheld resonator that the player can use to amplify particular frequencies, which we hear as distinct musical notes. To learn a bit more about trumpets, I actually went and bought one just for this video, and here it is. This is my second-hand etude trumpet that I bought online. I have no idea how to play it, and honestly, I can barely even make it make a noise, so I won't be playing it today. The player blows into the mouthpiece, causing their lips to vibrate. The resulting pressure wave travels into the lead pipe to the third valve. This valve controls whether air is allowed to continue flowing normally to the rest of the trumpet or diverted into this additional tubing. The number 2 and number 1 valves perform a similar function with their own respective sections of tubing. Once the air exits the number 1 casing, it's allowed to flow into the final piece of tubing, which leads to the trumpet bell, and eventually the sound waves propagate into the atmosphere. We can model this in the computer as a series of tubes with 3 valves in the middle. As you can see, the trumpet functions very similarly to the example earlier, and it can be thought of as a variable length pipe. Depressing the valves makes the tube longer with a lower resonant frequency, which we hear as a lower pitch. Handling the interior of the simulation with Tubular is fairly easy since it's just built-in components like pipes and junctions. The only part that's a bit exotic is the mouth and lips. A lot of the trumpet's characteristic sound comes from the way that the lips vibrate inside the mouthpiece, and there are entire research papers written just about this phenomenon. The lip simulation I'll be showing today is based on the model presented in this paper, Trumpet Sound Simulation using a 2-dimensional lip vibration model, written by Seiji Adachi and Masaaki Sato in 1995. They outline a very simple model where the lips are assumed to be masses held to a fixed point with 2 springs, which makes logical sense. Simulating this is very easy because it's just a typical harmonic oscillator. Since it's 2-dimensional, it captures both the horizontal and vertical movement of the lips. The model also accounts for the forces acting on the lips, like the pressure inside the mouthpiece, the pressure inside the mouth, the elastic and damping forces from the lips themselves, and the Bernoulli pressure acting on the bottom of the lip. All of these pressures are pulled directly from the fluid simulation, so we don't have to model or calculate those separately. In the paper, the trumpet itself is modeled using a convolution filter with a measured impulse response of a real trumpet. According to Reddit experts who criticized me for doing this exact same thing with the original engine simulator, this is not a real simulation, so we're going to be replacing this filter-based approximation with an entire CFD model of a trumpet using Engine Simulator's fluid simulation. Visualizing the trumpet using this simplified interface can be useful, but it's not the most exciting experience ever. Considering that I spent many weeks studying fluid simulations and staring at math all day, I decided to spend a few days doing something completely different by making a 3D trumpet model in Blender. I like to do this from time to time. I don't really like working on the same project for too long, and I don't really like working in the same field for too long. So sometimes I'll switch over from programming and do more of an artistic project. In this case, it was actually relevant because I can use it in my game engine to actually show the trumpet and kind of demonstrate the way the Engine Simulator's fluid simulation is going to work. So it was not a complete waste of time. So here's the end result. There are some smaller details that I just didn't really bother modeling because they're not necessary, but this is good enough for my purposes. And this was rendered using my ray tracer, which I showed in one of my older videos. With that completed, it was time to work on the 3D Fluid Visualizer, which is going to be used both in Trumpet Simulator and Engine Simulator. The fluid visualization is critical to the gameplay experience of Engine Simulator, so I put quite a lot of thought into what it should do and how it should work. The visualization that I showed previously in this video seems okay at first glance, but the problem is it doesn't really show fluid velocity very well. And this is very important when you're studying engines. In fact, it's essentially impossible to see the motion of the fluid unless there are sharp temperature or pressure fluctuations being pushed across the domain. My original plan was to implement a particle-based system very similar to what I implemented in one of my older videos. I laid the groundwork for this a few months ago by adding instancing to my Vulkan game engine, which allows for the rendering of some very high polygon 3D particle systems. I chose particles for a few reasons. The main reason is that it's very easy to convey fluid velocity in this way. I think it's a lot easier, especially for a casual audience, instead of showing, like, for example, a vector field or just arrows pointing in the direction of the velocity. It's a lot less entertaining, and it's not really very intuitive to look at. This point is less important for engineering and scientific applications, but since I'm targeting a more general audience, presenting the results in a visually pleasing way is a lot more important. The implementation of the visualization is fairly straightforward. It's basically a collection of particles released into the fluid system, and they can be moved around by the airflow inside. Interestingly, the visualization itself is a simple physical simulation of point masses in a fluid. So we're using a simulation to interpret the results of another simulation. These particles can either be spawned in randomly or injected at a certain point, like smoke in a wind tunnel. The particles also change color depending on temperature, and they also change scale depending on pressure. To clearly show pressure and temperature, I also added the more standard pressure and temperature display that we discussed earlier, and it follows the length of the tube. For PCs that maybe don't have a lot of GPU capacity, displaying tens of thousands of particles at a time might be a little bit excessive, so I do have some backup visualization schemes that the user can choose from, or they can just turn them off completely. Before I show you what this sounds like, there are a few things that I want you to keep in mind. First of all, some very important elements of the simulation are not yet in place. Right now, it's assumed that the Trumpet has a completely cylindrical bore with no cross-sectional variation, which is obviously not correct. The simulation does support variable cross-sections, so it is possible to model the Trumpet's flare and the bell, and I have been able to successfully simulate things like two-stroke expansion chambers. But the implementation isn't really complete yet, and it wasn't ready for this video. Without taking the trumpet bell and flare into consideration, the trumpet's intonation is seriously messed up and you can't really play music on it. Another thing to note is that the lip model has many parameters to control, as does the rest of the trumpet. So playing this thing is not as simple as plugging in a MIDI keyboard and then playing random notes. Just like a real trumpet, you have to adjust the blowing pressure, your lip geometry, the lip stiffness, and the trumpet valves themselves, and doing this effectively on a keyboard is not that easy. So the most I can play for you guys right now is a simple chromatic scale and just a few random notes to show how the trumpet handles transient effects. We're mainly interested in the general character of the sound anyway, just to validate the fluid model. The most amusing part of this simulation for me is the fact that it just sounds like a computer that is really bad at playing the trumpet, as opposed to the usual problem of computers sounding extremely robotic and synthetic. There are still some very obvious issues, which I haven't really solved yet. For some reason, the computer has to blow way too hard into the trumpet to actually make a decent sound. I don't know how to play the trumpet myself, but my understanding is you shouldn't actually need to blow such a massive quantity of air into the instrument. But for some reason, just the model works better when you do that. Obviously, the multitude of parameters need a bit more tuning before this thing is ready for the stage. But it is cool to see how the parameters affect the character of the sound. Here are a few demonstrations. So first we can just try blowing way too hard into the trumpet and see what happens. We can also adjust the lip parameters to emulate other instruments. So this, for example, sounds a lot more like a clarinet or some other woodwind instrument. Up to this point, the audio is coming directly from the trumpet simulation with absolutely no post-processing whatsoever. I'm just sampling the pressure near the end of the tube and playing it back as an audio signal. We can apply a bit of convolution reverb to make the trumpet sound like it's in a real space, like a concert hall or something, and this enhances the immersion quite a bit. There are truly limitless ways to adjust these parameters, and the fact that they're all physically based makes the process very intuitive and engaging. The most exciting thing is that everything that I showed in this video will be possible to do directly in Engine Simulator. The only component which is a bit non-standard is the lip simulation, since I can't imagine why you would need that when simulating an engine, but everything else is just standard valves and tubing. There isn't anything special going on. This means that players might be able to build and test virtual musical instruments in a physically realistic way in a game. Now I'm going to stop myself here before I start making too many crazy promises, but so far everything is looking very promising. My computer isn't slow or anything, but I'm running hardware that's over 5 years old now, and I can run this demo at hundreds of frames per second with no trouble whatsoever. Anyway guys, that's it for this video. I hope you enjoyed it. I don't intend to leave Trumpet Simulator in this sad state, and it will continue to evolve alongside Engine Simulator since they both share a lot of the same code. It's a great testbed for testing audio code and fluid simulation changes. I will be releasing this demo to my Patreon members, and if there's enough interest, I might consider releasing it on Steam. I'd like to thank all my supporters on Patreon and NordVPN for sponsoring this video, and thank you for watching. I'll see you guys next time.